Welcome to another session of differential geometry class. Today we are going to discuss about the parallel transport and the concept covariant derivative. So first of all, a definition. This we have already seen. A vector field X along a parameterized curve alpha from I to S in an n surface is said to be tangent to S. What you're considering is a vector field along a parameterized curve, and we will say that that is tangent to an n surface along alpha if x of t, that is your vector field, belongs to the tangent space at alpha of t, right? So you are having a surface over here and here the interval, okay, AB. Now from AB we are having a curve, so somewhere here it should be. So this is your alpha. Now you take an t over here, corresponds to that t, you are having the image here as alpha of t. Now you consider the tangent space at this point. Tangent space at this point alpha of t. Now if your given vector field belongs to this s of alpha of t, then we will say that this given vector field is tangent to the n surface along the curve alpha. So here we should point out one remark. The derivative x dot, we used to mention like that, x dot of a vector field x which is tangent to s, along a parameterized curve alpha, comma, a parameterized curve need not be in general tangent to S. That is, suppose some vector field is given and which is tangent to a surface along alpha, so that doesn't imply that the given vector field is tangent to the surface. It's given that tangent to S along alpha, so it doesn't means that it is tangent to the surface. But here the fact is that we can have this we can define a vector field which is tangent to S also. So when you are considering a picture like this, okay, so this is my S. Now I am having x dash of t. So somewhere here I am having a vector called x dash of t. Sorry, x dot of t. Sorry for that. It's not x dot. Okay, so this is x dot of t. X dot of t it is, and we have got his normal as n of alpha of t. This normal is n of alpha of t. So somewhere here is my alpha, right? So this I can take as s of alpha of t. Now if we are projecting this to this surface, what you're getting is, here you will get another vector, right? So this vector, I'm naming this vector as x dash of t, and we will say that this is the covariant derivative. So actually what we have done is, from this s of alpha of t, we can resolve this into n of alpha of t and a tangent vector. So from the component of x dash of t, we have avoided the component of n of alpha of t. Normal component we have deleted. That's why it belongs to the tangent space, right? So in general, tangent to s. However, however, we can obtain a vector field tangent to s by projecting x dot of t orthogonally onto s of alpha of t for each t belongs to I. For each t belongs to I, we are projecting x dot of t orthogonally into s of alpha of t. So we'll get another vector x dash of t, and this x dash of t is, we will say that this is the covariant derivative. So definition: let S be an n surface. Let S be a n surface in Rn plus 1. Let alpha from I to S be a parameterized curve. In S, and let X be a smooth vector field. Let X be a smooth vector field tangent to S along alpha. The covariant derivative of x, the vector field x, is the vector field x dash tangent to S along alpha, and denoted by how we are defining? As I said, we have to delete the normal component. So x dash of t should be equal to x dot of t minus x dot of t times n of alpha of t. So means this is the normal component, right? So that much of times n of alpha of t. So we want to minus the normal component. So x dash of t, that is the covariant derivative of a given vector field, is given as x dot t minus x dot t dot n of alpha of t times n of alpha of t, where n is an orientation on S, where n is an orientation on S. So covariant derivative is defined as x dash of t, and that x dash of t is equal to x dot t minus x dot t dot n of alpha of t times n of alpha of t. That means we are avoiding or we are deleting the normal component from x dot of t. Thus the covariant derivative, thus the covariant derivative x dash of t is the orthogonal projection onto the tangent space of the ordinary derivative What is that? X dot of t. So x dash of t is the orthogonal projection onto the tangent space of ordinary derivative x dash of t. Now properties of covariant derivatives. Properties of covariant derivatives. Properties of derivative we have already discussed. So similar to that, we are having the properties of covariant derivatives also. So let x comma y be two smooth vector fields tangent to S along alpha, and let f be a smooth function then property number 1. So x and y are smooth vector field tangent to S along alpha and f be a smooth function. Then the first property is x plus y dash covariant derivative of sum of two vector fields is nothing but x dash plus y dash. And second one, fx dash So this is f dash x plus f x dash as our product rule, right? And third one, x dot y dash is nothing but x dash dot y plus x dot y dash. So I will prove these two. This I'm leaving for you to work. So first one, x plus y dash of t. Use the definition. So by definition, this is nothing but x plus y dot of t minus x plus y dot of t minus into n of alpha of t into n of alpha of t. We are making use of the definition of covariant derivative, nothing else. This definition only we are making use it here. Now we can split this. That's equal to x dot of t plus y dot of t minus, this can again we can split this into x dot of t into n of alpha of t, right, plus y dot of t into n of alpha of t times n of alpha of t. Now we can split this x dot of t minus, from here you take x dot of t times. So x dot of, that is this term, x dot of t into n of alpha of t times n of alpha of t, right? So n of alpha of t. So this is the first term, plus another term is similarly this y dot of t, y dot of t minus, I should consider here y dot n. So y dot of t into n of alpha of t times this n of alpha of t. Now by definition, this will reduces as x dash of t. Similarly, this will reduces as y dash of t. So this is equal to x dash of t as to x dash of t plus y dash of t. So we have proved that one. Okay, the first one we have proved. Now what about the second one? Second one is f x dash of t. That's equal to, again using the definition, it is nothing but f x dot of t minus f x dot of t, f x dot of t dot n of alpha of t times n of dot with this with n of alpha of t. Okay, now this is equal to, we can again split this using the property of derivatives. So this is f dash of x plus f x dot, right, of t, the first term, we are making use of the product rule for this. Minus, here also we can split this, f dash of x plus fx dot of t dot with n of alpha of t times n of alpha of t. Okay, so this can be written as, we can combine f dash terms and f terms, right? So when you are multiplying these two, we will get like that. So this is equal to f dash of x, right, of t minus, I'm considering the f dash term, so f dash of x, right, f dash of x into t dot with n of alpha of t times n of alpha of t. Now this can be written as, oh sorry, so one more term is there, no? So f x dot of t minus, next term I should consider this term, right? So f x dot, right, fx dot of t dot with n of alpha of t times n of alpha of t. So this term will reduce as f dash of x. Here we are having x of t dot n of alpha of t, right? So this is equal to f dash of x of t okay, this is equal to f dash x plus fx dash of t. Why it is reduces like this? Since x of t is dot with n of alpha of t is equal to 0. So which term will get reduced as f dash of x t, this term as such, plus, see here some x of t dot n of alpha of t is coming, so that should be 0. So the remaining term is f x dash of t. This f can be taken outside, so f into x dot of t minus x dot of t dot n of alpha of t times n of alpha of t will come. So this will reduces as like this. So this term will be 0 here. That's why this term is 0. So you can write it like this. So we have proved the second property also. Third property I am leaving for you to work. So the third one is a homework for you. Next I am going for a remark. The covariant derivative x dash measures the surface, the rate of change of x measures the rate of change of x along alpha as seen from as seen from the surface S by ignoring the component of x dot uh, normal to S. This means, as we have said, we can actually take the rate of change of x. Suppose this is a surface. Along the normal direction, we can check. See if this is the normal direction, means along this direction is changing now. So like that also you can measure the rate of change. Another way is that we can take is tangents. Okay, so in this tangent position also you can take how it is varying, or we can take the rate of change. So when you are talking in terms of covariant derivative, means this normal components is not the, so this is not the, this is not the, this is not the, this is also not the. So one can visualize this rate of change in terms of its tangents. So in terms of tangents means from this surface only we can visualize it. So it says that the covariant derivative x dash measures the rate of change of x along alpha as seen from the surface S. Next we have got a small theorem here. Theorem. A parameterized curve alpha from I to S is a geodesic in S if and only if its covariant acceleration how we define covariant acceleration means alpha dot of dash is zero along alpha. So we want to prove that a parameterized curve alpha is a geodesic. What was geodesic? So acceleration is everywhere orthogonal to S, right? So the geodesic in S, if and only if its covariant acceleration is zero along alpha. So proof: let alpha from I to S be a geodesic in S. Then alpha double dot of t belongs to S of alpha of t perp. That's the normal space, right? For every t belongs to I. Now alpha dot dash of t, right? This we want to find now. That's equal to, by definition, this is alpha double dot of t minus alpha double dot of t dot n of alpha of t times n of alpha of t. Since alpha double dot of t belongs to S of alpha of t perp, what do you get? We can write our alpha double dot of t as a multiple of n of alpha of t. So alpha double dot of t is equal to some g of t into n of alpha of t. Means a multiple, right? Where g from I to r. Hence, alpha dot dash of t can be written as, first term was alpha double dot of t. This alpha double dot of t can be replaced with this. So that's equal to g of t into n of alpha of t, right, minus g of t into n of alpha of t, right, dot with n of alpha of t times n of alpha of t, right? Now what is n of alpha of t dot n of alpha of t? G of t is a constant, right? So this will be unit normal. So when you're having normal, sorry, dot product, it will result 1. So this is equal to g of t into n of alpha of t minus g of t into 1 into n of alpha of t, right? So this is equal to g of t into n of alpha of t minus again g of t into n of alpha of t. So what you're getting is equal to 0. So we have proved that whenever your alpha is a geodesic, then its covariant acceleration is 0. Now we want to prove in the other way. Therefore the covariant acceleration ration is 0 along alpha, right? Along alpha. Now we want to prove the converse part. So conversely, what we want to assume? Covariant acceleration is 0. So conversely, suppose that covariant acceleration alpha dot of dash is a 0 along alpha, along some alpha. Then what you're having is alpha dot dash of t equal to 0 for every t belongs to I, which implies alpha double dot of t minus alpha double dot of t dot with n of alpha of t times n of alpha of t equal to 0 for every t belongs to I, which implies alpha double dot of t is nothing but alpha double dot of t dot with n of alpha of t times n of alpha of t. So this is a scalar one, right? Dot product means it's a scalar one. So this implies your alpha double dot of t is a multiple of n of alpha of t, right? So this implies alpha double dot of t belongs to the normal part, that is s of alpha of t perp for every t belongs to I. So for every t belongs to I. So what does this means? This means alpha is a geodesic in S. So we have proved that whenever its covariant acceleration is 0, then alpha is a geodesic. So in today's class, we will discuss the concept of covariant derivative. So first of all, the covariant derivative, a vector field along alpha need not be tangent to the surface, but we can go for the covariant derivative so that we will get a vector tangent to S. Next, how to find this covariant derivative means covariant derivative is equal to from the derivative part you remove the normal component. Then properties, three properties are there. Then a theorem, a parameter is equal to alpha is a geodesic in S if and only if its covariant acceleration is 0 along alpha. So hope you understood the concept covariant derivative. Let us have more discussion in the next class. Thank you for your patient listening.